Hello everyone, this is Seth Schaefer from Team Just Cause Robotics, and today I would like to make a fairly long tutorial video on a topic that is probably pretty central to the entire idea of combat robotics, and that is spinning weapon design. You'll note that Division has two, and actually I've just designed a third now, different spinning weapon configurations. I've switched between a disc and a bar that I designed at the exact same time, more or less, in different fights since the first iteration of this robot. And I'll talk about what the advantages and disadvantages to each of those are later on, but for now, I'd just like to basically give an overview of what are the different factors, both in terms of the math and physics behind it, and in terms of actual, fighting robots in general, that impact how I designed my spinning weapon. And I'll also go into just the general, theory, briefly at least, so I don't bore you to death with math, of what actually is the goal of a combat robot spinner, and how to make one that is actually good for a particular type of robot. So, in this video, I'm pretty much only going to talk about two different types of robots, horizontal spinners and vertical spinners, because these comprise the vast majority of combat robots with spinning weapons, and generally speaking, they have a very similar goal. That goal is transfer energy into your opponent. When you get into combat robotics, there are a few terms that get thrown around a lot when talking about spinners. MOI, or moment of inertia, kinetic energy, or KE, RPM, which is the rotation speed, revolutions per minute of the weapon, bite, which refers to how much tooth engagement you actually get on your opponent. And then also you have to worry about gyroscopic forces, especially when you're talking about with vertical spinners. Much less so with horizontal spinners is that really a concern, but it is still a thing to worry about. And then another number that gets thrown around very often is tip speed. Tip speed is really kind of a weird metric to think about when you're designing a spinning weapon, because at the end of the day, it's actually almost utterly meaningless. What really matters in terms of transferring energy into your opponent is the kinetic energy of your weapon and the amount of bite that you're getting on your opponent. It actually doesn't really matter what the mass of the weapon is nearly as much as the moment of inertia, because the amount of kinetic energy stored in a weapon is 1/2 j omega squared. Omega is the scientific letter that defines revolutions per minute, or in the way that we'll actually do the calculation, radians per second, which is the revolution speed of your weapon. J stands for the moment of inertia, or MOI, for your weapon. So, how do I know what the MOI of my weapon is? CAD. There's pretty much no way that you'll ever be able to, by hand, calculate what the moment of inertia of any weapon that isn't a bar with just a series of holes in it by hand, other than CAD. But it makes it super easy to do it in CAD, because I just right-click on the body that is the blade, and make sure the material is set correctly with the correct density, and then bam! I get my weapon mass and the moment of inertia about the center of mass, which is what we care about. So in this case, you can see the x-axis is the in line with the weapon axis, so we only care about IXX here. So that is 6.1 times 10 to the 5th grams millimeters squared. I've switched everything to metric right now because it's easier to convert to joules when you're dealing with metric. So what exactly is the kinetic energy storage of my weapon disc for Division at the absolute peak speed? Well, we have 1/2 times I, or J, which is IXX in this case, so 6.107 E5 grams millimeters squared, don't worry about the units, they'll work out, times my RPM. So in this case, my motor turns at about 30,000 RPM, because I'm running it on 3S and it's a 3000 kV motor. I have it geared down almost 3-to-1, so my weapon turns at about 12,000 RPM with it at full throttle and the battery fully charged. So we actually need to convert that, so 12,000 RPM to radians per second. I'm using a plugin, so every time I type equals space in this search bar, it automatically goes to Wolfram Alpha. So that's 1257 radians per second. Ah, yes. So radians are a unit that kind of drop out of calculations, I forgot. Okay, so we get a result of 482.5 joules. If I were to be running the weapon at like half speed, let's say 6,000 RPM, that would be 628.3 radians per second, which results in 120.5 joules. So you'll notice this is 1/4 of what it just was with the speed doubled, and that's because the speed term is squared. That is incredibly important to note. The RPM that your weapon is running at contributes twice as much to its total kinetic energy storage as your weapon's moment of inertia. And the weapon's moment of inertia is dependent not on the weapon's mass by itself, but actually it's essentially like the average distance away from the central axis of your weapon that the mass is located at. So in other words, the further away the mass is, the more it contributes to your moment of inertia. So this weapon weighs 250.9 grams. Let's look at my bar weapon. So this bar is a little bit lighter, as you'll see. So the bar has a mass moment of inertia of, now we're again in the x-axis, so 5.271 times 10 to the 5th. Moment of inertia at the origin doesn't matter. Moment of inertia at the center of mass is all that matters. So again, we're in the ix-axis, so 5.271. So it's a bit lower. So here, it's a bit lower than before, because we went from 6.107 to 5.271. So yeah, the bar is a bit less MOI efficient than the disc, and it's also a bit lighter. So both of those kind of hurt it a little bit, but still, we're over 400 joules of energy storage, and that's not bad. 482 is, you know, considerably higher than 416, but both of these weapons have a decent moment of inertia. However, I've recently designed a new weapon. This new weapon is modeled after the lightweight version of Deep 6. Right here, designed by Dustin Espwine, the same exact guy who built the heavyweight version of Deep 6. So we can see here, this weapon has a really weird shape to it. Yeah, so this robot just bounced itself all over the freaking arena, and it's like half of its weight is in the weapon. It's 25 pounds, and it only spins at 3,500 RPM. That's kind of slow, you would think, but given the size of the weapon, it really starts to add up. One of the major benefits to this weird weapon shape, however, is that it's really, really moment of inertia efficient, and I'll talk about why that is shortly. So first, let's look at my version of that. So this is my Deep 6 modeled disc type asymmetric weapon. So the first thing that is a major benefit to this design is that it is asymmetric, which means that it only has one impactor. So if I draw my 7.5 inch circle here, there's about 3/4 of an inch or more away. So this is, I believe that is 6 inches, and then it's 7.5 inches effective diameter, which means that, you know, this point is 3.25 inches away from this point. So, get rid of that. Why is this better? Well, let's look at the moment of inertia. So I have it set to the same AR500 steel density. It is 254 grams, so pretty much the exact same as the disc. Let me double check what exactly the disc was again. So the disc is 250.9 grams, 251 grams. So it's 3 grams heavier, But I mean, that's not like a ton, right? But let's look at the moment of inertia. So here we're looking at IYY, 8.94 times 10 to the 5th. Yeah, it's a bit higher. So at the same 12,000 RPM, we went from just shy of 500 to over 700 joules. This weapon will hit about 50% harder than the disc at the same RPM. And that's purely due to the way that the mass of this weapon is distributed about its center. The goal to weapon design shape-wise is basically just get the mass as far away from the central axis as possible. The more mass that you have further from the center of mass, it all contributes the most to moment of inertia. So that's why this is more efficient. So you have this huge tooth, which is as far away from the central axis as possible. There's a lot more mass in this tooth than there is in the mass of the teeth on my disc. And then I also have as much mass as possible concentrated in this section here. So you can see in the Deep 6 one, it's actually pretty much the same thickness here, here, and here. I made it so that it's considerably thinner here and here. These actually taper slightly. They're actually not, that's not aliasing because these are like straight and it's at an angle. That's actually, by design, this tapers down just to make it so that I could put even more of the weight that would have been in these spokes into this bulge here. And then I actually just continuously tweaked all the size of these fillets and these fillets until I got the center of mass to be pretty much dead on where it should be. So I think it's within 1/1000th of a millimeter of the actual center of this weapon. I'm sure in real life, once it's laser cut, there will be more variability than there is in CAD, but it's pretty damn close. Like, you can literally see properties. I think it tells you, yeah, here. So the center of mass. So the center of mass is negative 0.000793 millimeters. So that's how far away it is from dead centered. Anyway, so there's this kind of like rule that Robert Cowan mentioned that I think is definitely not like originally sourced from him, but something that's kind of like generally recommended, that you put maybe 30% of your robot weight into the weapon. The best way to maximize that, like the effect of that weight, is to maximize the MOI, because you can see here I did 3 grams to a 250 gram weapon, and by just changing the shape I have 46% more kinetic energy storage in that weapon. So why do I want an asymmetric weapon? Is bite. Basically, tip speed is way less important than your RPM when it comes to bite. It can still be good to know, but when it comes to bite, the only things that matter are the speed your weapon's spinning, how many impactors it has, and how fast your robot's moving towards another robot when you're colliding. This webpage has pretty much all the information you will ever need, and more than just what I'm going to talk about in this video, and it pretty much goes into all of this. But essentially, bite is the maximum depth of opponent insertion into the arc of a spinning weapon at a given RPM and forward velocity. So basically, in theory, your weapon is rotating around and around and around as the opponent is coming close to you. So as this weapon turns, imagine that my robot's driving forwards and an opponent's coming along, right? Some amount of time passes between when the weapon's here and then getting back to here. If I had only one impactor, it's the time between getting here and then all the way around to here. So essentially, you get twice as much bite with a single impactor as you get with 2 impactors at the same RPM. Because if this is rotating 12,000 times per minute, 12,000 RPM is 12,000 revolutions per minute. So how many times are those impactors going to cross the point of my robot that could hit an opponent per second? Well, we have revolutions per minute, and we want to turn it into impactors per second. So that's just 12,000 times 2 impactors on my disk per minute times 60 seconds per minute, right? And we get 400 hertz. So 400 times a second, 400 times per second, this tooth is going to cross into the path that it could hit an opponent. If I only have one impactor, now it happens 200 times per second. If my robot's forward velocity is the same in both of those cases, which, I mean, it is, because spinning my weapon faster or slower doesn't make my robot drive any faster or slower. Let's say that my opponent is standing still. I drive my robot forward as fast as I can at them. The maximum amount of tooth engagement that I will ever get is dependent on the speed at which my robot's moving forward and how many times the impactors cross it per second. So both of my bar and my disc have 2 impactors, and at the same RPM, that means that those impactors are whizzing by the same point 400 times per second. If my robot is driving forward at, 10 miles an hour, then let's say that I'm going 10 miles an hour. I've got 12,000 RPM, 2 impactors. That means there is 2.5 thousandths of a second in between times that weapon's going across, which means my maximum bite is 10.6 millimeters. If instead I have one impactor, my maximum bite doubles to 21.3 millimeters. If my robot's not driving at full speed, like let's say it's only going like 6 miles an hour, I don't actually know what the top speed of my robot is, but it might be considerably less than 10 miles an hour. Now we're down to 12.8 millimeters, and with the 2 impactors, all the way down to 6.39 millimeters. That's a little over a quarter inch. 6.35 millimeters would be 1/4 inch. So personally, in my opinion, a quarter inch of bite is about the minimum that I'm willing to accept, around 6 millimeters. And in all of my fights thus far, I pretty much never run my weapon at full speed because of this, because this is actually your max bite. So your realistic bite, it's kind of like a probability thing. So the chances that my weapon's here at the point that my opponent is right there, and it just misses them, and then the entire half revolution goes by with them continuing to drive towards me before I hit them, the chances of that happening are slim to none. So on average, let's say my weapon is here when my opponent gets to the point where they're just outside the arc. On average, I'll get half as much as the maximum possible bite. So that's why it becomes especially important that I'm doubling it by using one impactor. Because now if I'm running at full speed, in reality, half the time, in reality, the majority of the time, I'm getting more like 3 millimeters of bite, not 6. If I push that to a single impactor, now I'm getting 6 millimeters of bite on the average case instead of 3. So that's a pretty significant difference. So bite's affected by the forward speed, speed of the opponent, as well as the time between teeth, like I just explained. Bite is a lot more critical for a horizontal spinner, especially against wedges, than it is for a vertical spinner. Why do I say that? Well, because most vertical spinners have a feeder wedge like this. So having this wedge makes it a lot easier to get bite, because you can get your opponent's lip up. So it allows your tooth engagement to increase dramatically faster than it would otherwise. So if they're just coming forwards at me, then it's their linear speed is the only thing that matters. But it essentially makes it so that instead of them having to go forwards, and it's like the difference between them being here and here, now we're talking about the distance between them being here and here, which will increase a lot faster than just like the 6 miles an hour that they're driving at me, because as soon as they touch this, they're going to like bounce up. So I'm essentially able to get a lot more for less bite than I would otherwise, because if you're catching like the front lip of a hardened steel wedge or a titanium wedge, even with only 1 or 2 millimeters of engagement, that point is still rigid enough on them for you to just frickin' launch them. With a horizontal spinner, you'll never really get that. Every time your weapon hits the opponent, you're going to glance off of them, and they're going to glance off of you. With a vertical spinner, when I hit my opponent, my bot glances off of them into the floor, so I'm not actually going anywhere, and they're getting launched into the air. So I say bite's more critical for a horizontal, especially against a wedge, where you're talking about you getting deflected upwards instead of them getting deflected the exact opposite direction as you, because you need to impart as much energy into them as possible, and you really, really need a lot of bite when you're hitting onto an angled surface to be able to deliver that energy efficiently. Your weapon needs to spin up reasonably quickly, because you want to be able to avoid getting totally screwed if you're getting box rushed by a wedge or whatever. So I would say you want under 5 seconds. My weapon's pretty massive, but I use an absolutely, like, stupidly oversized motor for it, so it spins up in, like, 3 seconds, and I literally can't push my motor to spin up the weapon as fast as possible, because the moment of inertia of the disc, especially, is so large that my entire robot's chassis wants to torque about the weapon axle, and it'll actually faceplant itself, which you can see if you watch my recent Norwalk Havoc video. Even with the bar, I think that happened. As I was trying to drive forward, the robot just frickin' faceplanted itself the moment that I tried to spin up the weapon, because it has enough force that it'll, like, literally bend these nylon forks 90 degrees. So then, yeah, generally 30% of weight for the weapon. I don't really know what this rule is trying to say, whether it's saying this one piece of metal should be 30% of the weight, which mine is nowhere close to that, it's actually a lot lighter than that, or should your weapon plus the pulley driving it, plus the weapon axle, plus the motor, plus the ESC for the motor, like, I don't know what really constitutes as weapon weight. In my case, I kind of went for, like, weapon motor plus weapon bar, and didn't really factor in, like, the pulleys and belts. My weapon motor is about 3 ounces, and the weapon discs and bars and such are around, 9 ounces, so I'm still not really close to the 16 ounces for that, but because I've maximized the MOI to the greatest extent that I could, and I've made sure to have a really good balance of, like, bite and, like, such for the weapon, my robot's able to hit pretty hard for how little the weapon really weighs. And it's weird to say that the weapon weighs little, given its, like, comical size, but really, you can think of my weapon as more of, like, a horizontal spinner-sized weapon. And then you kind of get an idea it's, like, actually not that huge. It's just rotated 90 degrees from how a horizontal spinner would be using it. It's honestly a pretty reasonable size for a horizontal spinner. So, maximizing KE without sacrificing bite. Because of that W squared, the omega squared term, you get a lot more bang for your buck by just spinning faster, but you have to prevent yourself from losing too much bite. And also, it's worth mentioning, if you're using a given motor, like you've already chosen what weapon motor you're going to use, it's only producing so much torque. And so if you have to make your belt ratio go from 3 to 1 to, like, 1.5 to 1, then that motor has to produce twice as much torque to spin up the weapon, which means your spin up time could be exponentially, it could be, like, quadratically longer, actually. It could go from 3 seconds to, like, 8 seconds, not just 3 seconds to 6 seconds. So there's 2 different trade-offs that you have to worry about with, or trying to spin your weapon at a higher speed. It literally is how much energy needs to be dumped into it. How much motor electrical energy is going to be consumed, turning that electrical power into mechanical power, and then how long that mechanical power needs to be sustained for before your weapon is at its maximum KE. So, if you think about it in that terms, you can kind of get a sense of, like, how it adds to the time. The heavier, the more speed you need to build up, the more kinetic energy that you need to build up, the more time it will take to build up to that level with the same size motor. And so you can compensate for this by, getting a bigger motor, but then you have to change up your pulley ratios and everything, and you end up in, like, kind of a back and forth of balance, like a balancing act, which a lot of things in combat robotics end up being a balancing act. Spinning weapon design is by no means an exception to that. You end up needing to balance a lot of different factors. But anyway, you need to the main 2 things you want to balance are your RPM and your loss of bite. And like I was saying before, the reason that I'm going to an asymmetric weapon is because that allows me to actually run the weapon at full speed and still have all of the bite that I'm getting at half speed with these weapons. So you can change your pulley ratios or motor KV to change speeds easily, but you want to keep your spin-up time in mind. And making the weapon significantly heavier isn't usually an option. It's better to just design a more MOI-efficient shape and proper bite/tooth size. So, like I was saying, that's why I've done this. That's why I've designed this weapon, is because I don't really have more weight to dedicate to my weapon. I have a whole robot chassis that's actually been performing extremely well. I would like to be able to run the weapon faster and get more out of it, because, you know, having this like huge beefcake motor isn't really doing me any favors unless I'm actually using it to its full potential. And if I actually run this weapon at full speed right now, I don't get enough bite, so I need an asymmetric weapon to be able to properly utilize the like potential of my weapon motor setup. So weapon shape. The most efficient shape would be a hollow tube with impactors on the outside, like many drums, especially in heavyweights. Why don't we look at a few heavyweights? Ironically, one of the few robots that actually does this the best is this one, Yeti. So Yeti actually uses a hollow aluminum tube with these like discs welded on the side that hold bearing blocks and everything. And this is actually a really efficient shape for MOI. You can hear Greg Gibson talk about this in one of the episodes in the early 4th season of Battlebots. Because it is hollow inside, that means all the mass is on the outside, which is, like I was saying before, pretty much the best possible scenario for having a really, really high MOI per weight. Next, we see Valkyrie. Valkyrie here has a weapon with a really terrible MOI, and a weapon that's been specifically optimized for really good MOI. So this weapon, called Dr. Teeth, has been modeled using some simulation tools to basically maximize its stiffness to weight and its moment of inertia to weight. And it's a two-tooth design, but you can see there's like a really weird kind of shape to it overall because of the fact that it used I think generative design to like generate these like weird natural curves and be as efficient as possible for the weight, but still have most of the mass towards the outside. This weapon here, which is a bar, is a lot less MOI efficient because a lot of that weight's in that central hub area. So this weapon spins up probably faster than this one, even if they weigh the same. Next, talk about Endgame, Deep Six, Copperhead, Black Dragon. All of these robots use asymmetric single-tooth designs so that they can spin their weapon as fast as possible, getting the highest KE possible, and not trade off too much bite. Endgame has this like triangular shape that's kind of like what my weapon design sort of looks like, my new weapon sort of looks like, but obviously without all the cutouts and stuff. They have multiple different weapon configurations. This one I think is the newest one. Deep Six, obviously this incredibly iconic massive bar with a significant amount of its mass pretty far from the end. This is kind of the same concept, just in a way that uses a material more efficiently, because inch-thick AR500 bars are expensive to get made. So this is sort of like, if you have to do a bar, this is kind of the way to go, where you have a huge block of material that's far away, and you use holes to get rid of the material that's closer to the center, if you can. Copperhead, kind of like a weird combo between an egg beater and a drum. Obviously also an asymmetric design. They have this huge tooth with a lot of the mass of the drum in it, and then you can see it's hollowed out inside, so that they can have as much mass here and here as possible to maximize MOI and have an asymmetric single-tooth design so that they can maximize their speed and KE without sacrificing bite. Black Dragon, kind of the same concept, with more of a traditional-ish looking egg beater design where there's just like one central cutout, but still huge amount of mass here, huge amount of mass here, and here they have blunt edges for extra impact without dulling a sharp edge that you might get from like Deep Six's like sharper corners here. I won't go into like rake angles or anything like that because that's a topic for debate that I don't fully understand like how you make those decisions. Bloodsport's an example of a horizontal spinner again. Here we have actually again a pretty inefficient MOI-wise design. I am working with the Bloodsport team now, and I can tell you that the weapons that we'll be bringing to Season 5, if it does happen, will be a lot more moment of inertia efficient than this, but this was cheap to make, and it obviously, like the Deep 6 bar, it doesn't use up like a huge disk of material. Like, it's a lot more affordable to make a bar like this, so that's pretty much the main reason that it was this shape before. But you actually get some positive rank angles, you can see here, so this is meant to more like grab into opponents. And the reason that they went with this is, like I was saying before, with a horizontal spinner, bite's really important. Being able to bite into like a wedge on the side of your, on the front of your opponent is really important. So having a positive rake angle like this can actually be pretty good for a horizontal spinner, but it comes with the trade-off of like the chances that the tips of your weapon will chip is increased because you have a sharper angle and there's like less material behind it, etc., etc. But I don't really want to go into that because I don't fully understand like what the ideal rake angles would be or how you would come up with that. This concludes part 1 of this 2-part series on robot spinner design. Please subscribe if you'd like to see the next part, and let me know in the comments if you have any other questions, and I'll let you know if they're answered in the second part, or I'll answer them directly if not. Thanks for watching.